Hey guys, welcome back. It's Miss Wilson again with a new lesson and video. So it's lesson 6, graphs of polynomials. So now we're going to kind of get a little bit more into the visual representation of polynomials when they are on a graph. So let's get started. Let's first talk about the characteristics of polynomial graphs. So a polynomial of a degree 2 or more has a graph with no sharp turns or cusps. So sometimes you'll hear polynomials called smooth graphs because they have like smooth curves. It wouldn't look anything like this, okay? So this is a yes example. And this one over here, which resembles a absolute value function, would be a no. Okay? So give you a second. Go ahead and write that in. All right, so now let's talk about the domain of a polynomial function. Well, polynomial functions go on forever in both directions. So your domain is going to be negative infinity to positive infinity. The range would depend on the polynomial function itself, but the domain we know will always be negative infinity to positive infinity for a polynomial function. Then the values of x for which f of x is equal to 0. Well, we talked about these before. These are called the roots or the zeros or the x-intercepts of function f. All right, so those are the characteristics of polynomial graphs. And now let's talk a little bit about end behavior. So in the first unit, we learned about end behavior in terms of writing it in notation. So if x approaches negative infinity, then f of x approaches positive or negative infinity, and so forth, right? Well, we're going to include some of that today, but what we're really going to look at is the different types of end behavior based on the degree of the polynomial, okay? So if we have a polynomial that has a positive leading coefficient and it's an even degree, so an example of that would be, let's say if I had x squared plus 4x minus 3. All right, so let's just say I had that as a polynomial. Well, what's important here is that the leading coefficient is positive and the degree of the polynomial is even, okay? So when that is the case, that means that you are looking at end behavior where both arrows are pointing up, okay? Now, this might not be what the actual function looks like, but this is just to give you an idea because really all that matters here is the end behavior, okay? We want to know what is happening at the ends as x approaches negative infinity and as x approaches positive infinity. So when you have a positive leading coefficient and an even degree, the end behavior will be as x approaches negative infinity. I don't like that. Let me fix that. Negative infinity. F of x approaches positive infinity. Okay, and we can see that here. So as x goes towards the negative, f of x or y goes up, all right? So let me finish my end behavior. As x approaches positive infinity, f of x also approaches positive infinity. And again, as x goes towards the positive, it goes up. All right, let's look at another example. So here we have a positive leading coefficient and an odd degree. All right, so we're over here. Positive leading coefficient and an odd degree. So if I was looking again at the first term of a polynomial, it could be something like 2x to the power of 3. Again, we have a positive leading coefficient, but my degree this time is an odd number. So that might look something like, so let's put in my arrows. So we're going to have a down arrow that's now going to go up, all right? Again, this is not exactly the graph for this polynomial. And, this polynomial can finish out and look like whatever. What we're really just concerned with is what the leading coefficient is. Is that positive or negative? And the degree of the function. Is it an even or odd number? Okay, so if we have a positive leading coefficient and an odd number, then our end behavior will be, for these types of graphs, as x approaches negative infinity, f of x also approaches negative infinity. As x approaches positive infinity, f of x also approaches positive infinity. And you can see that in the graph. As we go negative for x, it goes down. As we go positive for x, it goes up. Okay? All right. So now let's look at even degree negatives. Well, if even degree positive was facing up, I guess you can imagine that negative leading coefficient even degree functions are going to be facing down. And if you guess that, you are correct. So again, this may look like a function like this, but instead of our leading coefficient being positive this time, it's now going to be negative, all right? So we're going to have a negative leading coefficient, and we're going to have an even degree. And both sides will be facing downward, okay? So let's see here. We would have as x approaches negative infinity, f of x approaches negative infinity. As x approaches positive infinity, f of x approaches negative infinity. Okay? And you can see that here, where as we go towards the left, it goes down. As we go towards the right, it goes down. And remember, these graphs that I'm drawing are not representations of the polynomial functions that I'm writing next to it. I am just pointing out, and if you want to see what these graphs look like, these particular functions that I'm writing, you are more than welcome to type them into Desmos to see what they look like. But otherwise, I'm just trying to show you what we mean by when we say negative leading coefficient or positive leading coefficient and even degree or odd degree, okay? So last but not least, we are going to look at the negative leading coefficient for an odd degree function. So again, this might be something that looks like negative 2x to the power of 3 plus x squared minus 4. Again, we have a coefficient that is negative, but this time we have an odd degree function, okay? And so this one will look something like this, where it starts going towards the left, going where x is negative, it goes up. Going where x is positive, it goes down. And so the end behavior for this would be as x approaches negative infinity, f of x approaches positive infinity, and as x approaches positive infinity, f of x approaches negative infinity. Okay, so here is the end behavior of polynomials. It would be beneficial to study this and try to remember this, because once you understand the end behavior and how to notate the end behavior and how to identify it in the function, it'll make your life so much easier. Okay. All right. So let's go ahead and hop to the next page. All right, guys, so let's now talk about the row zeros of a polynomial. So if f is a polynomial function and a is a real number, then the following statements are true. X equals a is a zero of the function f. X equal a is a solution of the polynomial function. X minus a is a factor of the polynomial function. A comma 0 is the x-intercept of the graph f. Okay, so let's have an example. So let's say I had x squared minus 7x plus 12. All right, I'm going to set this equal to 0. I'm going to go ahead and factor this. So if I factor this, I would have x minus 3, x minus 4, okay? Because negative 3 times negative 4 gives me positive 12. Negative 3 plus negative 4 gives me negative 7, which is my b coefficient. All right, my b term. So that also means that my x-intercept, well, first let's find out what my x's are. So x minus 3 equals 0. X minus 4 equals 0. So x is equal to 3. X is equal to 4. And then that means that I would have two x-intercepts, and my x-intercepts would be at 3, 0, and my x-intercepts would be at 4, 0. All right. And if I were to, let's say, plug this into a graphing calculator or Desmos, then I should be able to see all of this. I should be able to look at my graph and I can see that my x-intercepts are at 3, 0, and 4, 0. I can see the solutions of the polynomial function. All right. So now let's talk about crosses, kisses, and multiplicity. Well, multiplicity refers to the number of times that a factor appears in a polynomial. Given a factor, x minus a raised to the power of k, where k is greater than 1, has a repeated 0 x equals a of multiplicity k, such that, now that's a little confusing, but don't worry, I will explain it so that it's less confusing. If k is odd, the graph crosses the axis at x equals a. If k is even, the graph kisses the x-axis at x equals a. All right? So let's find all of the real zeros of these upcoming functions, okay? So we're going to do what we just did for the example above, and then I'm going to talk a little bit about multiplicity. And don't worry, we're going to combine the crosses, kisses, and multiplicity with finding the real zeros, and it'll all make sense by the time you're finished your notes, all right? So I'm going to find the real zeros of x cubed minus 6x squared, here we are down here, plus 9x, all right? So first thing I'm going to do is I'm going to go ahead and set this equal to 0. All right. And then I'm going to see, is there something I can pull out, like a common factor that I can pull out of each of these terms? Well, I can. I can pull out an x out of each of these terms. And if I pull out an x, that'll leave me with an x squared minus a 6x plus 9. All right? I still have an x here, but I can go ahead and I can factor this quadratic a little further. So this would give me x minus 3 and x minus 3, because negative 3 times negative 3 gives me 9, and negative 3 plus negative 3 gives me negative 6. So that means that I can take this and I can put these together, because it's technically being multiplied by itself, right? So x minus 3 times x minus 3 would be x minus 3 squared, and that equals 0. And by just looking at the value of k, right? So here's the k that we were talking about. So by just looking at the value of k, I can tell the multiplicity of this particular 0. So what this means is this 0, whatever that 0 would be, of x minus 3, hint, hint, 3, happens twice. So since it happens twice, the graph will touch the x-axis there. It will not cross it at 3, but it will touch it. It'll kiss it, okay? If I took all of these and I set them equal to 0, so if I said x is equal to 0 and x minus 3 is equal to 0, and I have a multiplicity of 2, so technically I have another x minus 3 equals 0. Then each of these would simplify to x equals 0, x equals 3, with a multiplicity of 2. Okay, so we have 3 zeros here. We have x equals 0, x equals 3, and we have another x equals 3. That's how we get a multiplicity of 2. All right, so let's look at another example. So I'm going to set this equal to 0. I'm going to look to see what I can pull out. Out of each of these terms, out of 2x to the power of 4 minus 2x squared, I can pull out a 2x squared. So I'm going to pull out my 2x squared. That's going to leave me with an x squared minus 1. I'm going to set it equal to 0 again. I'm going to fix my, feel like my little minus sign was touching that 1. There we go. So I can break this down even further. So I would get 2x squared, and then I would have an x plus 1, and I would have an x minus 1, and that equals 0. And so again, if I were to pull these factors and set them equal to 0, so 2x squared equals 0, x plus 1 equals 0, x minus 1 equals 0. Well, there's a couple of things that would stand out to me. Well, first, I would look at my k value. So again, here's my k, that x squared. So that means that I'm going to have 2 x equals 0s. So I'm going to have an x equals 0 with a multiplicity of 2. I'm also going to have an x equals negative 1, and I'm going to have an x equals positive 1. Okay, so if you need to, take a moment, pause, look at it again. Make sure that you understand exactly where we're getting these zeros from. Because that's important. If you notice, we would have a total of 4 zeros. So we would have 2 zeros for x equals 0, and we would have a -1 and a +1. And again, our highest degree here is a 4, so we would need 4 zeros, okay? That means at the graph, this would touch, and at the graph, these will cross, okay? All right, so let's start looking at these functions on graphs, all right? So this is where everything is going to just really start coming together, including the end behavior and the crosses, kisses, and multiplicity. All right, so for example, A, we have x to the power 3 plus 2x squared plus x. So I'm going to take x to the power 3 plus 2x squared plus x equals 0. I can pull an x out of each of these because they each have at least one x, each term does. So that leaves me with an x squared plus 2x plus 1 equals 0. I can break down x squared plus 2x plus 1 even further. And if I were to do that, I would have an x that comes down. But then I also have an x plus 1 squared. Okay? Because otherwise it would be x plus 1 times x plus 1. So that means that the x, if I set each of these equal to 0, right? So if I had x equals 0, and then I would have an x plus 1 equals 0, and I would have another x plus 1 equals 0. What that means is it would simplify to an x equals 0 with a multiplicity of 1. Since it has a multiplicity of 1, it's going to cross the graph or the x-axis. Then if I have an x equals -1, this has a multiplicity of 2, so it's going to kiss the graph at the x-axis. All right, so I'm going to go ahead and graph this. So I'm going to make some little tick marks here. And I know that it's going to go through at 0, and something's happening here at -1. But in order to determine what my graph's going to look like, I also need to talk about the end behavior. So what is the end behavior? Well, let's go back and let's look at my function. Well, my function does not have a negative in front of it, so that means that we have a positive leading coefficient and we have an odd degree. So we are positive odd. Well, if we think back to our notes before, a positive odd function or odd positive function is going to start downward and then go up, okay? And according to my multiplicity for each, it crosses at 0, but it kisses at -1. So that means I'm going to go up here to -1. I'm going to kiss the graph at the x-axis, but not cross it. I'm going to bounce off, and then I'm going to move up here, okay? Now, how low that bounce off goes, you can actually maybe plug in some values to see. But as long as the end behavior is correct and the behavior at the x-axis is correct, then usually we're happy with that, okay? So if I finish my end behavior, it would be as x approaches -infinity, f of x approaches -infinity. As x approaches +infinity, f of x approaches +infinity. All right. So that's how we combine everything that we talked about today in sketching the graph of a polynomial. All right, so let's go to the next problem. All right, so I have f of x is equal to negative x to the power 4 minus x to the power 3 plus 2x squared. I'm going to set it equal to 0. And that's just something that I do out of habit. Then I have negative x squared. I can pull out of each of those terms. I can pull out at least an x squared. All right. And I'm going to do a negative, so that way it's a little easier for me to factor the quadratic that's left over. So I'm going to have x squared plus x minus 2 equals 0. All right, so that leaves me with a negative x squared as one of my factors. And then I can factor this quadratic even further with x minus 1, x plus 2. And by just looking at this, I can tell that I have x equals 0 with a multiplicity of 2. So that means it's going to kiss. I have an x equals 1 with the multiplicity of 1. So that means it's going to cross. And I also have an x equals negative 2 with a multiplicity of 1. And that's also going to cross, okay? So now that I have that information, I can go ahead and start drawing my little tick marks. So this time I'm going to put 3 since it goes up to negative 2, or goes down to negative 2. All right. And I'm also going to go ahead and write in my end behavior so I can start my graph. All right, so this time I have a negative coefficient but an even degree. So since I have a negative coefficient and an even degree, so we are looking at even negative, that means that it's going to be facing down. So I'm going to have 2 arrows that are going to be facing downwards. It has a multiplicity of 2 at 0, so that means it's going to kiss the graph there. It has a multiplicity of 1 at negative 2, so it's going to cross there. And then it has another multiplicity of 1 at positive 1, so it's going to cross there too. And again, if you want to know how high these curves go, you are more than welcome to check it out by plugging in some other numbers. Like you could plug in negative 1 into this function and see what it equals. All right, so your graph should look something like this. And I'm just going to finish it off with my end behavior. So as x approaches negative infinity, f of x approaches negative infinity. As x approaches positive infinity, f of x approaches negative infinity. Okay, so there's your notes. I know that this video was a little hefty. It had a lot to it, but as long as you take your time, review it, and ask Mr. Clement and I if you have any questions, you should be good. All right, so last thing for you to do is to go ahead and review them and come up with a summary about the graphs of polynomial functions. And I'll see you guys next time. Bye.